This unit of study is on digital fluoroscopy, and we're going to look at the continued evolution of dynamic imaging. Objectives are to describe and compare the advantages of digital fluoroscopy versus the image-intensified equipment, and also to describe the components and functions. Digital fluoroscopy was developed in the early 1970s by independent researchers at the University of Wisconsin and the University of Arizona, and it was used mainly for vascular imaging procedures. This included an added feature of digital subtraction angiography, which was used to obtain images of blood flow through the arteries. The systems that we're familiar with have image intensifiers with analog to digital converters. These dynamic images have the ability to be post-processed with window and level to be able to view various shades of gray. The newer units that use digital are used in specialized applications such as vascular imaging because the anatomy requires fast acquisition and great spatial resolution. The biggest differences between flat panel and image intensified fluoroscopy is the increase in contrast resolution. The spatial resolution is still limited by the pixel size of the display monitor during the dynamic imaging. The spot images themselves have higher contrast resolution, and the flat panel designs require less radiation and they're more sensitive to X-rays, meaning that the dynamic range of the number of photons detected is greater in the flat panel design. So looking at these two images, which one has the larger matrix? Well, the answer is 1024, because remember that the larger the matrix, the smaller the pixel. The main difference between conventional fluoroscopy are these two components, the CCD or charge coupled device and the use of flat panel detectors to acquire the dynamic images. The CCD is a replacement for the camera tube that was mentioned in prior modules, which operate under the name of Videocom and Plumicon. The flat panel detector is either direct capture configured with amorphous selenium, or indirect capture that uses cesium iodide amorphous silicon. Does this sound familiar? The indirect capture system can use the cesium iodide as its scintillator, or sometimes gadolinium oxysulfide, but then the amorphous silicon is the photodetector, and it's basically painted on a substrate material like glass. The TFT operates the same way as it did in static digital imaging. In digital fluoroscopy, the image receptor is 20 by 20 or 40 by 30. Sometimes it's 40 by 40. Images are acquired rapidly in frames and as high as 30 frames per second. So this is the image of a basic CCD array. There are fiber optics, which are very thin threads that act like light collectors. The cesium iodide is the scintillating phosphor, and this is coated onto the glass substrate. The light photons move through the fiber optics to a photoconductor that gives the light intensity its own charge. This charge goes through an analog to digital converter, ADC, to the video recorder and the monitor for viewing. And all automatic brightness control systems are still in use when CCD arrays are there. So here's an image that kind of puts it together. It operates in a similar manner to an image intensifier. The X-ray photons are captured. They're made into light by a phosphor on the input screen. A photocathode changes the light photons into electrons. And there are also these charge electrostatic lenses that move the electrons towards the output phosphor. Remember that in the tube there's always a cathode and anode that carries large differences in energy. And this creates a potential difference which is needed to move the electrons to the fluoroscopic screen, to the fiber optics, to the ADC. Apologies for the dark image intensifier graphic, but you understand from prior modules what they look like. The idea is to recognize that the CCD can act like an image intensifier, or it can be part of the output window to collect the light photons. So the TFT is an array of electronic components that are layered onto, again, a glass base. And this array includes a readout, a charge collector, and other light-sensitive elements. This is configured within a network of pixels, or more accurately, they're called detector elements, or DELs. And then all of this is covered by a scintillator glass plate. Each pixel contains its own photodetector, or photodiode, of amorphous silicon, and a TFT. So this means that the X-rays will be absorbed by the scintillator, and then they're converted into light photons. The photodetectors absorb the light, and then they convert it to an electrical charge. And then this electrical charge is captured by the TFT array and is transmitted to the display monitor. So it's been mentioned that digital fluoroscopy acquires images in a frames per second mode. So this is for a non-intensified system, one that uses a flat panel technology. The frames themselves can be thought of as many fast images that were acquired, almost like looking at a flip book when you're viewing the images. Pulsed fluoroscopy images are used with an image intensifier, and they turn the exposure on and off at a quick rate. This lowers dose as well. Masking is used in digital subtraction angiography, and it uses the frames per second mode. So the system is maybe set for 15 images per second for 4 seconds. That means that there's a total of 60 images that are going to be obtained over the 4 seconds. A base image is acquired, and then several image frames with contrast added are combined to create the subtracted image. This is referred to as image integration. So the flat panel detectors are more commonly reserved for these specialized uses in cardiac vessel imaging or interventional procedures. They're being added as conventional imaging solutions when image intensifier fluoroscopy equipment ages and needs replacement. So it'll allow the patient to have a lower dose but also a higher dynamic range. Detector sizes are 25 by 25 or 40 by 40. So these can capture images at 60 frames per second. And this can occur because the signal can be read line by line in fractions of a second. Noise in an image in fluoroscopy is common. So there's an application-specific integrated circuit called ASIC, and that is used to minimize noise and to amplify the signal. So again, this helps to lower the dose. The smaller size and weight of the flat panel detector, they allow for easier manipulation and then greater access to the patient during the fluoroscopy exam because of less bulk. The spot images are operated at regular static imaging MAs of 100 to 1200. The dynamic and static images can be archived into packs, but they do have large file sizes. Static spot images can be about 8 megabytes a piece, and dynamic images can be as large as 240 megabytes per second. There are many other advantages, and they're listed on this slide. And basically, you should understand that spatial resolution is the same for all systems, but it is better than the image intensifiers, which have a spatial resolution of 2.5 to 3.2 line pairs per millimeter, and the digital systems have 1 to 2 line pairs per millimeter. This follows the same concept as in film. It's really the contrast resolution that has improved with digital imaging. The operating dynamic range is 60 times greater than with image intensifiers. The rectangular and flat shape of the image intensifier removes that vignette distortion seen with image intensifiers. And again, the dose is lower because of the pulsed beam, meaning the X-ray is on and off in a frame-like sequence using higher MAs. Magnetic steering of catheters is now made possible with flat panel detectors because they are less sensitive to magnetic force flux or fields. This is a really new technology that uses a magnetic tipped catheter to move through tortuous vessels while a magnetic flux is applied. So this also will reduce radiation doses in the future. Federal guidelines for fluoroscopy equipment regarding the QC and laws can be found in Title 21 of the Code of Federal Regulations. So fluoroscopy inspections are basically performed every 6 months at a minimum. The American College of Radiology, ACR, recommends about 18 characteristics of fluoroscopy that should be evaluated by the physicist at that time. So the operational checklist is here, and some of the little comments are when the bucky is moved to the end of the table, you're moving it out of the way of the underlying tube, and the cover that's on the edge of the table should expand to lower the exposure to the personnel. And then the other is the lead curtain that's on the outside of the table. It should be able to be moved freely. And all the carriage controls should work easily, so no unnecessary time is spent with the fluoro on. The exposure switch should work, as well as the dead man switch if overtime is used. The shutters should be the size of the field of view, and they must be accurate within plus or minus 3%. The timer should produce an audible alarm after 5 minutes of on time. This time is recorded. And a penetrometer is used to adjust monitor brightness when it's placed on a phantom image. The goal is to see as many shades of gray on the pentameter image as possible. And then the table tilt should operate smoothly with the correct angle displayed. So these tests are the same as the QC that we use for static imaging equipment, with the same kind of tolerances for beam alignment, exposure reproducibility, timer accuracy, KVP accuracy, half value layer. Those are just a few of the 18 items, but there are some items specific to the fluoro, which includes the dose area product meter calibration, video and viewing monitor performance. This concludes our module for digital fluoroscopy.